howdy. This is Mr. Potter. We've been talking about using power series, using geometric series, using Taylor series and Lagrange series to estimate the results of polynomials on some given interval. The issue, of course, is that these are estimates. So the question then becomes, well, just exactly how good is the estimate? And in order to do that, we need to take a little bit of an analysis of what the errors are. And of course, ideally, we'd want to try and find some way to bound these errors, to find some way to control how far off we are from the given value. So I'm going to start by taking a look at a geometric series. We've talked for the past few times about how the series 1 over 1 minus x is really equal to 1 plus x plus x squared plus x cubed plus x to the fourth plus x to the fifth plus so forth. Adding up terms that are x to the n. And this equality holds as long as x lies between -1 and 1. This is our interval of convergence that we've mentioned several times. But what I want to do is I say, what if I was to just stop at the fifth term? In other words, if I was to stop here and use this as my estimate, that means that all of this from this point on would be my error. But if I take a look at those error terms, the first term of that sequence is x to the 6th. The next term of that sequence is x to the 7th. The next term of that sequence is x to the 8th. And what I notice here is that this is another geometric sequence. So this is another geometric series with my first term being x to the 6th, and so my sum is the first term over 1 minus my common ratio. In other words, this is my error. This is how far off I am by terminating at a fifth degree polynomial to estimate 1 over 1 minus x. In other words, I can come up with an exact formula that represents how far off I am. And so when I'm dealing with geometric series, it's very easy to determine what the actual error is going to be, because the tail of a geometric series is in of itself an infinite geometric series. It has the exact same ratios we had before. The only thing that's different is this initial term, which in this case is x to the 6th. So in other words, I can come up with an exact formula, how much off I am for a geometric series. Now, when I'm talking about Taylor and Maclaurin polynomials, it's not so easy. So I want to go back to Taylor's theorem. Remember that Taylor's theorem says that I can represent a function on some domain by using the sum from n equals 0 to infinity of the nth derivative at some point a in the domain times x minus a to the nth power divided by n factorial. And when I do this, I'm going to have all of these terms, but similarly, if I was to terminate at some point, the points beyond that are the tail of the series, and that tail of my series is my error. But keep in mind that because n factorial grows so fast, my tail of my series tends to be dominated by whatever that first term is. And what Lagrange's error bound actually says, Lagrange, the error bound, says that my error can actually be determined to be less than or equal to some expression of the next term in this sequence. So if I'm looking at a polynomial of degree k, my next term would be the nth derivative, which is really be the next term would be k plus 1th derivative at some point c, where my particular value of x has to be within in other words, c has to be within x minus a times x minus a to the k minus 1 plus 1 power over k plus 1 factorial. Now this part here and this part here are exactly the same as Taylor's theorem. I'm still looking at the x minus a to a power over that self-same factorial. The only thing that's different is I'm not necessarily looking at a being the argument of my k plus 1th derivative, but some value c inside of this interval. What we'll find, however, is that looking at the next term gives us a very reasonable bound for what we're dealing with. And so I wanted to do an example of this. Let's say I want to use a 5th degree polynomial to estimate the sine of 2. So if I'm looking at this, I know that the sine of x, according to the Taylor's theorem that we've come up with, centered at x equals 0, gives me x minus x cubed over 3 plus x to the fifth over 5 minus x to the 7th over 7 factorial, of course, plus so. So if I wanted to terminate here and just let this represent sine, if I wanted to say that the sine of 2 is approximately equal to 2 minus, this is really 8/6 plus, this is going to be 32 over 120. If I want to use this to represent the sine of 2, my error is actually going to be less than or equal to the absolute value of this next term. In other words, 2 to the 7th power over 7 factorial. And so this Lagrange error bound really gives me a lot of understanding of what's going on here. And one of the things that we've noticed about both our sine and our cosine polynomials is that they tend to approach the sine and cosine values very, very quickly. Even if we're only looking at a 5th or a 7th degree polynomial, just looking at the first 3 or 4 terms. If I was to actually calculate this, that's 100 and, it's 128 over 7 factorial is 5,040. And this decimal is 0.025. So in other words, the error that I get for terminating at this polynomial, terminating at a 5th degree polynomial to estimate the sine of 2, I'm actually less than 0.025 off. And so that's very convenient for me. So I want to do one more example of this. Let's say that I'm trying to deal with e to the x. I want to use the first 5 terms to estimate e to the 1/2 power. So if I'm doing that, remember that e to the x is equal to 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial plus etc. Now, if I want only the first 5 terms, I'm really terminating here. And that means that my error is going to be determined by the next term in this sequence. In other words, my error is going to be determined by this. So my error is actually going to be less than or equal to the absolute value of 1/2 to the fifth power over 5 factorial. Now 1/2 to the fifth power, that's 1/32. And 5 factorial is 1/120th. So I actually end up with something here that's about 0.000026. And if I look at e to the 1/2 on my calculator and compare it with this, I find that I'm very close to this error. In other words, for AP purposes, I'm close enough to AP accuracy with only dealing with a fourth degree polynomial. So this is the power of these power series. The fact that they do tend to converge very, very quickly. They do tend to give us very good estimates, even though I'm only using about 4 or 5 terms in the polynomial. So, this is Mr. Potter. Thank you for watching. Have a great day.